Hello students, you all are warmly welcome to another chemistry lesson. Here we are going to continue. It's regarding the electronic configuration. It belongs to the first unit. Hope you were with us there in our earlier lesson. Students, we started talking about filling of electrons there inside of those atoms, calling it the electronic configuration. So students, we are going to continue the same lesson further. So we are about to find out how those atoms are bearing electrons there. Though we are calling that filling of electrons inside of those atoms, actually atoms have already got their electrons. It's just for us, for our knowledge, for easy study, we are calling this as filling of electrons there inside of those atoms. Otherwise, atoms already are having electrons. So, hope atoms know this, that I am doing such a lesson like regarding them, those filling of electrons inside of atoms. Those would say that no, we already have electrons. Okay, students, in our earlier lesson, we found that out what is the quantum theory, quantum model regarding the atom. So, representing the structure of atom, we finally found that out, the quantum model. Okay, so let me start the lesson regarding the filling of electrons inside atom. It's the electronic configuration. Further we are going to focus on writing of quantum number sets. Okay students, when you check for where do we have this lesson in our syllabus, it belongs to the competency level 1. Students, when you check these electronic configurations, you could find it belong to the competency level 1, which discusses uses electronic arrangements and energy transactions in determining the nature of matter. So, it has a further subunit, means we call it competency level. Okay, so it belongs to the competency level 1.3, 1.4. So, you could find there states the evidence for electronic energy levels of atoms. In 1.4, it says states the ground state electronic configuration of isolated, means gaseous atoms, and not only atoms but also ions as well. Okay, so as the subject content under this topic, you are going to find that out. Students, we are having these principles and rules relevant to the filling up of electrons where? Inside of those atoms. Students, there it's Hund's rule, Pauli's exclusion principle, then Aufbau's principle, and its deviations in the higher atomic numbers. There are a few deviations as well. We are going to consider them. So, students, then further we are having as the subject content, students, ground state electronic configurations of isolated gaseous atoms of elements of atomic numbers from 1st to 54, those elements and their ions as well. Okay. Then further we are going to find out this brief introduction to 4 quantum numbers. We are going to write a quantum number set regarding the position of those electrons and the way those electrons you find they are within an atom. Okay. So, we are calling that a quantum number set. We are going to find it out. What are these quantum numbers? The principal quantum number denoted by simple n. The azimuthal quantum number denoted by simple L. It is called angular momentum quantum number as well. So, its magnetic quantum number denoted by M, in small you have simple L. So, the spin quantum number, the spin direction that you have their electron there within an atomic orbital is given by spin quantum number. So, it's denoted by simple M with S. Okay. Okay. Those are the stuff we are going to have here in our lesson today. Okay. I am ready now to present you about writing of electronic configurations. So, it's the matter whether you are ready. Okay, students, get ready to find out, consider their electronic configurations that you have within those atoms. When you check for electronic configurations, we follow this principle, what we call Aufbau's principle. We call it the build-up principle as well. Electrons are filled inside of those atoms in the order of energy. Increasing order of energy, ascending order of energy. It's the ascending order of energy of their, are they shells? No. It's of their subshells energy. You would find energy is getting increased in their shells as 1, 2, 3, 4, 5. It's the Bose theory says, Bose theory, Bose model explains that you have electrons being filled inside of those energy levels in the increasing order of shells energy. But it's after Niels Bohr, they revealed that the existence of subshells. You have SP, DF, various such different subshells there, found out there within shells. In the first shell you have one subshell is this. In the second shell you have two subshells, those are S and P. In the third shell you have three subshells, those are SP, D. In the fourth, it's obvious, it's four subshells. From fourth onwards, it's four subshells are SP, D, F. So it follows the order of not the shell's energy but the subshell's energy. Students, it's the increasing order of energy is found there in subshells. So it's the ascending order of their subshells energy. You could find this out. Electrons being filled inside of those atoms. Okay, when we say like that, it's now a matter whether these subshells energy are different from shell's energy. Let me explain that as well. Students, when you talk about the subshells, those shells get split into subshells. As I have already mentioned, it's the first shell consists of one subshell only. It's the S subshell. Let's call it 1s. Okay. Then it's having one atomic orbital. It's spherical shape, S atomic orbital. Then having three atomic orbitals which have dumbbell shapes, you have P subshell as well. Additional to S there you find they are within second shell. Then I could state that its second shell could be found being split into what? It's into two subshells as S and P. Then further when it comes to third shell, it's 3S, 3P, 3D are the SPD. Those are the subshells. So when it comes to fourth, it's SPDF. Other subshells, those get split. But when it goes away from the nucleus, with increase of energy, there are gaps between shells. Going to get decreased. With that, students, we could find out it's been quite messy. So when it goes to upper energy levels, their lower subshells would be quite lower than of upper subshells of lower energy levels. It's the upper subshells of lower energy level. So what I'm saying is 4s is further lesser in energy than 3D. It's the third shell, lower shell. Its upper energy subshell is 3D. Then it is the fourth shell, greater in energy than third shell. So its lower energy subshell is 4s. 4s is lesser in energy than 3D. For this reason, it's very hard to predict that. It's the same that 1, 2, 3, 4, that order that you find those electrons being filled inside of atoms, inside of shells. No, it's not. It follows the increasing order, ascending order of their energies of subshells. Then students, how we could obtain this order of increasing energy of subshells? It's in our earlier lesson, on our last day, also I explained this. So let me go through that. Students, when I give you that, you could find that out, the energy is getting increased in this order. It is, you find 1s first. You fill maximum number of electrons that you could fill there in 1s. Then after, it's you go to the second 2s. Then fill that and then go to the 2p, then 3s, 3p, then it is not 3d, it's 4s, then after only you find 3d, then it's 4p, it's 5s, then after 4d, 5p, 6s, it goes like that. Okay, then you might wonder how could we obtain such an order of those increasing in energy of those subshells? Students, in that, you could follow a method like this. You write all the subshells, you state all the subshells that belongs to one particular shell. This is your first shell, this is the second shell, and this is third, fourth, fifth, sixth, seventh. You could go ahead. So students, if you have electrons only, you could go ahead. So students, then, it's your first shell is carrying 1s, the subshell only. Then second shell is having 2s, 2p. Third, 3s, 3p, 3d. And fourth, 4s, 4p, 4d. And 4f, bonus one. So you are having such subshells getting increased up to fourth. Then after it would be the same. There would be 4 subshells. They are within each shell. Okay. Then students, you could find out this order drawing a diagonal here. So you continue drawing parallel lines there and there as well. So it follows this direction. It follows this direction in the increasing of energies, their energies. So you could link one to another in this manner. So students, it's 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, it's 4d, 5p, 6s, it's 4f, 5d, 6p, 7s. See how easy? But in the exam, so you do not need to draw such a kind of pattern and obtain the order. Then is that you need to by heart that? No, it's last day I explained that. Hope you could remember. Let me remind that again. Students, it's the same order that little while ago what I have drawn. So it follows this order of energies of their subshells that you could find out. So let's write each shell's energy, each shell energy shell subshell. Like it's the first shell here, it's the second shell here, it's the third shell here, it's this one and this one belongs to fourth shell, and it's fifth, and you could continue sixth. You write those subshells as one after another of each shells. Let's call that the normal order. It's not normal, but let's call it the normal order. Okay, then students, when we are finding out what's the fill-in order, you could give them as it is SP, D, F. The increase in order of their energies, that if those SP, D, F subshells belong to the same shell. So S is the least in energy. Then you find P, then you have D, then you have F. Okay. Then you start filling those subshells in their normal order. You follow the normal pattern. So there you fill 1s maximally with 2 electrons. Hope you know that fact. Any S subshell could be filled maximally with 2, P could be filled maximally with 6, it's D maximally with 10, and it's F maximally with 14. So students, you fill maximally those subshells, right, when you keep following. So it's you fill 1s with 2 electrons. Then after, if you have further electrons, you fill them in this manner. When you are worrying which one is to be filled next, you check what have you filled for the last time. It's a S. Then you check whether you have any lesser energy subshell than S. Do you? No, you don't. Then you follow the normal order if the answer is no. Okay. So you don't have any further lesser energy subshell than S. So you follow the normal order. After filling then 1s, you follow filling of 2s. Then if you have further electrons, you check what is the one I have filled last. It's a S again. So it's you don't have lesser energy subshell than S. Then you follow the normal order. It's 2p. After being filled 2p with 6 electrons maximally, if you have further electrons only, you do this. Students, it's what have you filled last? It's a p. So do you have any lesser energy subshell than p? Lesser energy subshell than p? Yes, yes, you have. It's a S. It's a S of next. You follow that order. It's a S of next. Then you follow S of third. Third is the next. Last you filled was 2p, no? Then next is third. So you fill S of third, 3s. After filling 3x maximally, 3s. Then you check whether you have further lesser energy subshell than S. No, you don't. Then you keep filling in the normal order. After 3s you have 3p to be filled. After filling 3p, then when you check for what have I filled for the last time, it's a p. Then you have a lesser energy subshell than p is a S. You then fill S of next. After third, it's fourth. You fill 4s, not 3d. You fill 4s after filling 3p. Okay. After completion of 4s, then when you check for whether you have any lesser energy subshell than S, the answer would be no. Then you keep filling those that you find in the normal order. In the normal order, you have already filled 3s, 3b. Then after you have filled 4s. Then after you start filling in the normal order, what you have left behind was 3d. You fill that. You fill that with maximally 10 electrons. So then after you check for whether any lesser energy subshell than d you have. Do you? Yes, it's than d, you have p. So you fill p of next. It's after filling 3d, you fill 4p as the next one. So after filling 4p, you fill 5s as the next one. So you keep doing that. If you find any further lesser energy subshell than last you filled, then you fill that of next. Otherwise, you keep filling the normal order, those in the normal order. That's what the method. In that you don't need to by heart any such a pattern. Hope you have got that. Isn't it easy? Okay. Students, these make easy the study of chemistry. It won't be a burden. You won't be frustrating, right? Studying these things. Okay. Students, it's last day, we started filling these. Hope you could remember that we randomly filled some elements with electrons. Let me do that on one. Let's take fluorine here. So its atomic number is 9, which says that neutral fluorine atom is carrying equal number of protons and electrons. Therefore, its electron number also is 9. So you have 9 electrons there in fluorine. So you fill 2 here. Then you fill another 2 here. It's 4 already taken. Another 5 only it remains. You fill them here. That's what we call the electronic configuration of fluorine. Okay. So let's randomly fill another one here. Shall we do it on silicon? Students, silicon's atomic number is 14, which says in neutral silicon atom, you have 14 electrons. Okay. Then students, you fill it in this way. 2, 2, it's 4, it's 6 here, then it's 10, it's another 4 you have, you fill 2 here, and another 2 you have, you fill those 2 there. That's what we call the electronic configuration of that particular. It's silicon here. Okay, so you could keep filling on these elements. Shall we do it on calcium now? Calcium's atomic number, you don't need to by heart, they would provide you if it requires. Okay, calcium's atomic number, students, it's 20. Says you have 20 electrons if it's neutral electrically. So it's 2, 2, 6, it's 10. Then it's 2, 6, it's 18. So before filling 3D, you need to fill 4s. So with 2 electrons. That's what we call filling of those subshells in their increasing order. increase in order of shell's energy. No, it's subshell's energy. That's what we call build-up principle or Aufbau's principle. We call it Aufbau's principle. Then students, it's after 20, then after filling 4s, then you need to keep filling electrons into 3D. Let me show you that. So, shall I start it with scandium? It's 21st. So, students, it's 2 to 6, 1s2, 2s2, 2p6, it's 3s2, 3p6, 18 electrons you have used. It's after filling 2 here, it's 20. Now, the one only you have, so you fill it here in 3D. So, when you have others means titanium, vanadium, chromium, manganese, you need to keep filling, doing the same on these. You need to keep filling. It's 2, 3, it seems 4, but it's not correct, it's wrong if you do that, it's 5 there. So, it's a deviation that this chromium exhibits. So, let me explain that again. It's after filling these all in the same way. All means it's 1s, 2s, 2p, 3s, 3p, 4s. After filling them till you reach 20. It's you could sort it. You could say that it's the electronic configuration of what's that element? It's argon. So, you could call it the compressed electronic configuration. It's given argon is this manner. It's up to argon. What's the argon's electronic configuration? Till then you have this being stated. But it's, you make that sure, it's when you write that in your book only, not in the exam. In the exam you write exactly in this manner. In the way that you find those shells, subshells first, you state what are the subshells that you find within each shell. It's within the first shell, second shell, third shell, fourth shell, fifth shell, like that. You state all the subshells. But when you are filling, you make that sure you are filling in the order of those subshells energy got increased. It's the build-up principle. In that manner only, you need to fill those electrons. So, here for our easy use, it's I am going to compress, means giving argon here, I am going to say till that it's you have argon's electronic configuration. So, till these you meet argon's electronic configuration. Then after it is argon's configuration, it is then after 3D and 4s you have. You fill 2 with 4s and you fill 1 if it is scandium only. It's 1 on 3D. Then you keep filling 3D as for scandium 3D1, titanium 3D2, vanadium 3D3. Then it's manganese 3D5. What about chromium? Regarding chromium, there is a deviation followed. Before giving you the deviation, let me explain what's the reason for this deviation it follows. It is followed by chromium. Let's find it out, the reason for the deviation that this chromium in future, you are going to find copper, not only copper, it's molybdenum and silver following. Okay, let's find that out, the reasons for that deviations that they are going to have with them, those elements with the atomic number 24th, 29th, 42nd and 47th. There you are going to find out some deviations. Okay, then before giving you that deviation, so let's learn this. It's what we call Hund's rule. What's the Hund's rule? Students, Hund's rule states that atomic orbitals within the same subshell are not paired with electrons until those get unpaired. All of those get unpaired. Those are not paired. What does it supposed to mean? Students, it's like you imagine you have a p subshell. Then if you fill one electron, I have denoted p subshell saying that you have 3 atomic orbitals there. I reserve each square for one atomic orbital here. Then it's symbolizing each atomic orbital. I have drawn 3 squares. Okay, so it's a way that you could symbolize them. Okay, then students, it's then when you say you are filling one electron, you give that electron there within one atomic orbital would be either spinning in one direction or the other direction. That spin direction, given that it's I will arbitrarily give it as a half arrow in upward, or otherwise I could give it downward but a half arrow there, symbolizing, denoting one electron there. Okay, if you have got one atomic orbital there within the p subshell being filled singly means with one electron, then it would not become double couple till all the other atomic orbitals are got filled with single electrons. That's the rule says. That's what the rule says. That's the Hund's rule says. Okay, so if you have got another electron, you please fill it either this one or this one. It's no matter which one. So you fill this one. It's no matter. There is no such order. So, but make that sure it happens in the same direction. Same direction it needs to follow. So otherwise it's not a must that you need to secondly fill second one and next fill third one. So who has named the second one exactly as we have those 3 of p atomic orbitals named as px, py, pz? Who could name it exactly this is the px, this is the py and this is the pz, as well as who could exactly say first you need to make that sure you fill px only. It's no one could say such a thing, like no one. Therefore you randomly fill, but make that sure it happens in the same direction as once you have filled one atomic orbital there. Whatever it is, it doesn't matter, you fill it, you make that sure it's having next in the same direction. Students, next electron you fill, they are not in a way like you couple. Let me further explain you. This is a d subshell. D subshell. You make that sure your first electron is filled inside of this or other one or other one or other one. Anyone you fill with first electron in any direction, it doesn't matter. It's you fill either in this way or in this way. Who cares? It's either in this way, right? So it's you have the freedom. You are fully free to fill your first electron wherever, in which direction, it doesn't matter. It doesn't matter. And in which atomic orbital also, it's we are not bothering about, but make sure you fill one electron for the first time. Then after, it's when you are filling your second electron, it's you shouldn't fill it in the same. It's you shouldn't fill it in this manner. That's the point. So you keep filling as if once it was filled in this manner in the same direction, and you make sure you fill it in an empty atomic orbital, making it unpaired still. So next electron you keep filling in the same direction till all the atomic orbital become unpaired. Then after you start pairing. You start pairing, filling it in the opposite direction. You could start it in any atomic orbital. It doesn't matter. It doesn't matter. So you keep filling till all become pairs. That's what the Hund's rule states. Unless you fill all the atomic orbital as those become unpaired, you can't start filling them as becoming paired. That's the point. That's the point. So then it's anyway we are having those that chromium's electronic configuration to be stated. So it's I'm going to talk about another thing. Students, when you start talking about a subshell, let's say a subshell is carrying atomic orbitals. A subshell is carrying one atomic orbital, P having 3 atomic orbitals, D having 5 atomic orbitals, and F having 7 atomic orbitals there. So within one atomic orbitals, when you start filling electrons, it's you need to follow the Hund's rule. Then regarding their electronic configuration in any subshell, it's you could find this out easily. Students, there are some electronic configuration regarding a subshell could call stable. Stable than others. Extra stable. What are the extra stable electronic configurations? It's when you get the subshell being filled fully, subshell being empty, and subshell being filled halfly. So fully filled, empty, halfly filled subshells are having such subshells are stable. Those are stable electronic configuration when you consider a subshell. Then students, it's the reason that we are going to talk about chromium differently. So it's when we talk about chromium's electronic configuration after giving argon, its argon comes till it's 18. When it is 18 electrons being filled, it's argon's configuration. Then after argon, it means that you have already filled 18 of electrons there. After argon, you fill, leaving 3D, you fill 4s with 2 electrons, then it's 20. When you talk about chromium, students, chromium's number of electrons it's having is 24. Another 4 electrons we have to fill there. So it seems like this is the way it is filled with electrons according to the build-up principle of Bauer's principle. But there is something having further. What's that? Students, though it's in this manner that those atomic orbitals within 3D and 4s. 4s is having 1 atomic orbital. 3D is having 5 atomic orbitals. Out of them, 4 are halfly filled according to the build-up principle of Bauer's principle. Then it's 4s fully filled. But it's not a whole subshell being halfly filled. But if we could make it halfly filled, this 3D subshell, we could make it stable. Then regarding that stability, thinking of that stability, one electron here jumps to 3D subshell, making it 3D 5, and now 4s is 1. It doesn't matter regarding 4s because 4s is having 1 atomic orbital. The only atomic orbital having it fully filled is stable, having it empty is stable, having it halfly filled also is stable, therefore it's stable. So then it gives a stable electronic configuration, exciting 1 electron from 4s to 3D. So I have mentioned it as Ns and this as N-1 D. For the reason you could imagine this as 4 and this is 3 for this time when it is chromium. Then I will explain that when it is molybdenum, students, this would be 5, this would be 4. Then also it follows that we call that a rearrangement. It follows that rearrangement. 1 electron get rearranged from 4s Ns2, let's say Ns2 to N-1 D4, making it Ns1 N-1 D5, giving it halfly filled stable electronic configuration. Therefore, when I go back to chromium story, students, it's regarding chromiums, I could write them, it's 1s2, 2s2, 2p6, 3s2, 3p6, 18. It's 4s, then 1 and 3d, this is not correct, 3d, 5. That's what. We call it a rearrangement. A rearrangement is followed there when it is chromium's electronic configuration. Then students, when we talk about others, I will randomly take another one. It's 27th. It's cobalt. So it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 20. Then another 7 you have. You fill all 7 here. So it's another pattern we could see from 21st to 30th. its 20 number is the 3D number. So those are exceptions, chromium and copper. I am going to explain regarding copper as well. So then for others except copper and chromium, students from 21st to 30th, 20 number is the 3D number in their electronic configuration. Isn't it easy? Seeing these patterns, you could enjoy a lot, right, in electronic configuration. Okay, then students, let's go to the copper story. So then it's 1s2, 2s2, 2p6, 10, 3s2, 3p6, 18. It needs to be, it seems like according to the Aufbau's principle, it needs to be 4s2 and 3d 9. But students, there we would find a stable electronic configuration. Let's assume this is the 4s2, this is the 3d 9. Then it is you lack one more electron here in 3d to become stable. It's if one jumps here, excite here, rearranges here, making it 3d10, 4s1. It is halfly filled S and fully filled D, a stable electronic configuration you could reach. There are also, it's at 29th and further in future 47th. There are also, you could find a rearrangement being made to make them stable electronic configuration. Those are therefore exceptions. Okay. So then it's giving it as NS2 and N-1 D9. Then students, when you are having this kind of electronic configuration to be written according to the Aufbau's principle, it's you better make one electron excite here and make it NS1 and N-1D 10. So it's reaching that stable electronic configuration, they get rearranged. Okay, that's the story. That's the story regarding copper. Then students, it's, let's go ahead. After copper, you have zinc. It's 1s2, 2s2, 2p6, 10, 3s2, 3p6, 18, it's 20, it's 10, 30. Okay, then gallium. It's 1s2, 2s2, 2p6, 10, 3s2, 3p6, 18, 4s2, 20, it's 3d10, 30, it's 4p1. Then from 31st to 36th, it would be 4p being filled, as in the pattern like, if it is 31st, 4p first. 32, 4p2, 33, 4p3, 34, 4p4, 35, 4p5, 36, 4p6. That's easy. That's very easy. Okay, after 4p6, what would it be? So up to that, I will give it as krypton, because when it is 4p6, students, it's krypton. Here you have, it is 1s2, 2s2, 2p6, 3s2, 3p6, it's 18, then 4s2, it's 20, it's 3d10, it's 30, then 4p6, it's 36. Then when it is 36, we could give it as krypton, krypton's electronic configuration. I could give it as compressed electronic configuration of krypton here. Starting from then, that I could continue. Okay. Then students, when it is 37, you would have rubidium. It's up to 36, it's krypton. So it's 4p6 being filled last, then 5s1. 5s is the next one. It's the 5x1. So it's 5s2 when it is strontium. Then after filling 5s as 2, then yttrium, zirconium, niobium, those elements would belong to 4D series. So you start filling then 4D as 4D1, 4D2 like that. Then you keep filling. After 5s2 it would be 4D being filled. Then it's, for a reason, I will skip filling of niobium. Then let's come to molybdenum. It has to be 5s2, 4D4. As we have earlier learned, students, there would be a rearrangement followed making it 1 and making it 5, bringing them stable electronic configuration, there would be a rearrangement followed. And here I am going to skip these. This it's 40, 43rd, 44th, 45th. I am going to skip those for a reason. It's anyway logically what we need to have are 5s2 43, 5s2 45, 5s2 46, 5s2 47 are the logical electronic configurations we are going to have. Stand in for them. But for the reason when it goes away from the nucleus, the gaps between energy levels get decreased, as well as the gaps between sub-energy levels also get decreased. Therefore, we could find out according to our logic, the Aufbau's principle, and further the deviations logic, it was thinking the stable electronic configuration. We got those two logics. It's beyond that, those two logics, it's quite illogical. Rearrangements also is going to be followed, as here one electron from this going to rearrange to this, making it 5s1 3d 4d 4. So its one would get rearranged from here to there, making it 5s1 4d what 6. It's quite illogical, the rearrangement followed. Here 5s1 4d7, 5s1 4d8. But we do not expect you to go thorough in these illogical rearrangements, but it's good to know. So students, when it comes to palladium, it's up to chromium, you have got filled them they are in that manner as 36 electrons, so it's then 38. Then when it comes to palladium, you have another how many electrons? It's 8 electrons remaining. So students, though it is the story of palladium according to Aufbau's principle, it needs to be, there would be 2 electrons, the only rearrangement regarding 2 electrons, with 2 electrons. There would be 2 electrons get rearranged here, making it 5s0 4d10, 5s0 4d10. It's another illogical, we could say, illogical rearrangement. So it's the only rearrangement with 2 electrons you could find here out. But we already have learned regarding 47th one, it has to be 5s2 4d9, but there would be a rearrangement making 4d10 and 5s1. It's fully filled D and halfly filled S, special stable electronic configuration given that. Then students, when you keep filling these, it's S2 4d10, it's S2 4d10, then when it is indium, it's 5p1. So S2 4d10, it's 5p2. So for others also, it's further 5p would be filled. 5p would be filled. So you could fill them all the elements now with electrons in their subshells, following that logic, that patterns, that let's say Aufbau's principle and special stable rearrangements. Okay, considering all those. Okay students, let's start talking about the electronic configurations of those ions. Ions means either gaining or losing electrons, they form ions, those atoms form ions. Then when we talk about writing of electronic configurations of those ions, first we need to consider the electronic configuration of not the ion but the atom itself. So when it is an anion, it would be not harmful, though you just find it out the total number of electrons and keep filling that. But there are also, you make a habit as you first go to the atom and start filling electrons on further electrons if it is an anion on that atom in their subshells. But when it is a cation forming, though electrons are got filled inside those subshells in the increase in order of subshells energy, there the removal of electrons need to be done as it's the decreasing order of their, not subshells now, shells energy. So you need to first remove all the electrons from the outermost shell, then after inner shell, in that manner. Okay, let me explain you this. Students, it's when you talk about the electronic configuration of Fe2 plus. Fe2 plus, its atomic number is 26, therefore it has to be 1s2, 2s2, 2p6, 3s2, 3p6, leaving 3d, so it's 4s2, then it's 3d, 6 when it is just iron. You first make that sure you write the electronic configuration of the atom itself. Then after, it is a 2 plus charge. It has removed 2 electrons. So students, it's not the same order, those electrons got filled, but it has to be in the order of those subshells and shells energy, not subshells energy. Students, you remove electrons from the outermost shell, not subshell. Outermost shell is 4th. You remove 2 electrons from this. So it has to be 4s naught, 3d, 6, while all the others are the same. That's what you need to do regarding their electronic configurations of cations. When it comes to chromium story, just chromium atom is carrying 3d 4s after rearrangement, 3d1 4s1 3d5 it has to be, 4s1 3d5 it has to be. Then when you remove electrons, you start removing from 4s 1 electron, other 2 you need to remove, you make that 3. This is the electronic configuration of Cr3 plus chromium 3 plus iron, is the method you need to follow regarding their electronic configurations of those cations. Students, when it comes to copper, let's start filling copper in the normal order. It's copper plus given, but let's first consider copper itself. So it is 3d 4s 3d 4s1 3d 10 after rearrangement. Then the outermost shell's electron is 4s, so it has to be 4s naught 3d 10. That's the method regarding their ions, cations electronic configuration. Let's go to titanium as well. Students, titanium being the 22nd element, it's after all those 4s 2 3d2, you remove electrons from outermost shell 4s, making it 4s naught, still 3d2. That's what you need to know regarding writing of ions electronic configurations. Okay, now I hope you know how to write the electronic configuration regarding those gaseous ions or when those atoms form ions. Students, we have come to our other topic. So we are going to give identities on electrons. We all are having our own identities. We all are having names, different names. It's not the same name I am bearing that you would have, isn't it? Okay, as well as we all are having different addresses. Okay, students, electrons, they are identical in all the aspects. If you have one electron here in your left hand, so and if you are carrying another electron with your right hand, so if you fold them in a bucket, right? So and if you, let's assume that electron size is quite bigger. So if you find that, if you try to collect that, pick that up again, so you can't recognize which one you were carrying with your left hand. Got my point? Students, electrons are identical in all the aspects. Then it's very hard to give identities on electrons unless we consider their positions within the atom. So regarding the positions that they are having, they are inside the atom, carrying. It's the shell, it's the subshell, it's the atomic orbital, as well as spin direction, giving those various positions that you find and the direction that you find regarding an electron that you find, they are inside of atom, we could give an identity. So we call it giving a quantum number set. Number set? Yes. It's 4 numbers you are going to mention there. Student, the very first number is called the principal quantum number based on the shell. Which shell it belongs? You give this. If it is first shell, we call it the principal quantum number is 1. Second shell, principal quantum number is 2. Third shell, the principal quantum number, not deputy principal, it's 3. It's in that way you give principal quantum numbers based on the shell, main shell they are having. Then secondly, it's what the subshell within that shell you are having this electron in. Based on the subshell, it's you give subshell quantum number. Any S you denote with 0, any P you denote with 1, any D you denote with 2, any F you denote with 3. So the second digit within this set stand in for the subshell. We call it the azimuthal quantum number or angular momentum quantum number as well. Students, it's the third. Within a subshell you find atomic orbitals there. So it's the orientation of those atomic orbitals we denote with this quantum number. What's that? Is that orientation quantum number? No, it's called the magnetic quantum number. The earlier, when it was azimuthal quantum number, it was standing for a subshell. A subshell would be different in shape, its atomic orbitals. What is a subshell first? Students, a subshell is gathering of atomic orbitals with the same shape. Therefore, a subshell would carry atomic orbitals having the same shape. Therefore, this second digit, second number, azimuthal quantum number, stand in for their shapes of those atomic orbitals. Then the orientation only is represented by this magnetic quantum number. So students, each subshell is carrying different numbers. When it is a subshell, it's one spherical atomic orbital. When it is a piece, that only spherical atomic orbital, we denote it with the value 0 for magnetic quantum number. Then when it is P subshell, it's carrying 3 atomic orbitals. 3 atomic orbitals. Students, those 3 atomic orbitals that within a subshell you are having would be carrying different 3 numbers. So let's first give 0, and its other 2 numbers are at 2 sides of 0 you find -1 and +1. The only atomic orbital you find within S subshell is 0. Then students, when you come to D subshell, it's carrying 5 atomic orbitals. So 1 you denote with 0. Then others you assign those values you find at 2 sides of zeros. -1 + 1, -2 + 2 are the other values. Then when it comes to F, it's easy now, you know what to do there. It's you first assign 0, 1 atomic orbital on 1 atomic orbital. Then you give other values you find as at 2 sides in this manner. So in that manner, it's you could denote their atomic orbitals with an address, with a value. So we call it the magnetic quantum number. So last, it's within 1 atomic orbital, maximally you could have 2 electrons. It's what we call Pauli's exclusion principle. What's that? So it's more than 2 electrons you can't expect within 1 atomic orbital. Simply it's that what Pauli explains. But students, further Pauli says that within the same atomic orbital, or within the same atom, let's say, you can't find 2 electrons carrying the same quantum number set. That's what Pauli's exclusion principle explains. So therefore, next is the spin direction. So when it is the spin direction, you give these 2 values. You denote one direction as with +½ the other as with -½ Those are the 2 values need to be given on those 2 electrons. Then combining all those together, we could write a set. A set of numbers, we call it a quantum number set, standing for one electron's identity. So the first number is simple n, is the principal quantum number. Second is the simple L, is the azimuthal quantum number. It is simple m with, it's the subscript, simple L. So we call it the magnetic quantum number. Simple m with subscript, simple S, we call it the spin quantum numbers. So this could take any value 1, 2, 3, 4, 5 such. This could take value 0, it's S, 1, it's not minus or plus, it's 1 when it is P, it is 2 when it is D, it is 3 when it is F. So then this takes values accordingly, as if it's a S subshell, then one atomic orbital only you find, you would have 0. If it's a P, it could either be 0 or minus 1 or plus 1. When it's a D, it could be either 0 or minus 1, plus 1 accordingly. That you have already found that out. You could give numbers. I'm not going to make it further complex. So it's either plus half here or minus half here based on the spin direction. That's what you have got. Then students, we have got those electronic configuration being coupled, combined with this idea quantum number set. So for an example, let's say this. For the outermost shell, electron of chromium. So we already know when it goes to chromium, it is 4s1, 3d5, including others. Others means up to argon. Then students, this is the outermost shell. So outermost shell of chromium is 4s1, is the last electron that you find. So you could give its electronic that electron's quantum number set in a manner like you have 4 the principal quantum number, it's a S the azimuthal quantum number, it's a magnetic quantum number, only one atomic orbital, it's 0, it's either plus half or minus half. So in that manner you could write quantum number sets, they are standing for electrons, their identities. Students, it's few simple ideas we talked about here within this lesson. So anything would come to an end, including this. So we have come to the end. Students, these are few easy simple points. So you follow these and you discuss matters arise regarding these with your teachers, and you could repeat watching these, they are in our YouTube channel NIE. Okay, students, with that, I'm going to finish the lesson here. We are going to wound up here. Students, goodbye.